Hey, what's up, everyone? So today we're going to be going over our market period 1 benchmark review. This is for geometry, ninth grade level. So our first question that we have, and now we're going back straight to the basics of vocabulary here. First couple questions are basics of vocabulary. It says, which geometric figures have a measurable quantity? Select each correct answer. So we're going to go down the checklist, right? First one says a line. I'm going to sketch an idea of a line here, right? Ooh, it's not straight, but pretend like it is. All lines should be straight. But key part about this line is these arrows at the end. The arrows mean that the line goes on forever, right? Can we measure forever? It says it has a measurable quantity. We cannot. It is infinite, right? Since it goes on forever in both directions, we cannot measure it. That is not one of our answers. What about an angle? An angle might be something that looks like this. Now, I'm going to ask you guys, what do we measure angles with, right? What do we measure angles with? Well, we measure angles with degrees. Let's say this is a 60-degree angle, right? Can we measure that? Yeah, we measure it with degrees. We could also measure it with this thing called radians, right? And gradients. There's a whole bunch of different things, but we can measure it. Next up, we have a point. What does my point usually look like? Our point usually looks something like this. Let's say we have point B. Now, that dot that's there just helps us visualize what this point looks like. We don't actually have a measurable. It has no length, width, height, any of that. So we cannot measure our point. Next up, a line segment. Our line segment should look something like this, right? It has two endpoints. Maybe we call that D, C, right? But we can measure line segments. This might have a length of 5 meters, right? We can measure that. It's 5 meters long. We have a measurement for that one. And my last one is a ray. When I think of a ray, I think of a ray of sunshine. It's starting at the sun. It's going out, boom, and it just keeps going that direction. Now, listen to what I just said. It keeps going. It keeps going. For how long? Forever, right? This is also infinite. Fun fact, this is a shorter infinite than our line up top. So we cannot measure a ray. So our answers for the first one is just an angle and a line segment. Let's go to problem number 2. Now, one thing I should suggest, and I didn't do it before the first problem, is try these problems by yourself first, right? Try to answer it first and then use my work to help you if you're stuck or to check your answers, right? You should not just be coming here and just selecting, oh, he did this, he did that, because then you're not learning, you have no idea what's going on, right? And on the benchmark or on your test, on your quiz, you're going to be out of luck. Then you're not going to know how to do any of the work for yourself, because these are not going to be the actual questions, right? These are not the exact questions that you might see. Maybe you'll see one or two. If you're lucky, maybe you'll see something very, very similar, but you won't see these 100%. So number 2, it says select from the drop-down menus to correct the complete sentence. Now, obviously, it's supposed to be a computer one, but I made it so it's on paper. The set of all points in a plane are equidistant from a given point called a blank. The given point is called a blank, right? So if we have a set of all points the same distance, now in my head, since I know this content very well, it sticks out to me what this answer is, right? We have a point and we have a set of points all the same distance. So maybe we have a point here, that is that distance. We have a point up here, that is that distance. A point over here, a point over here, a point over here, and here. If I connect all these points and we just keep doing points even closer and closer, it's going to give us this shape. Oh, mine's rough, but I think you guys could see what that shape probably is. It's going to be a circle. Now, the given point is going to be our center of the circle. That is the center right here, the center, right? And that distance is our radius. I know it doesn't ask us that, but this is our radius. That's the distance that all those points are away from that center. Let's go to our next one. Select from the drop-down menu correctly to complete the sentence. Given the distance non-collinear points A, B, and C, the set of all points between A and C, including A and C, is blank. So we need to break this down. So we're given 3 non-collinear. That means not on the same line. So I'm going to put A, B, C, right? Yours could be anywhere, but the thing is, if we want to connect the 3, we have to make a turn. We have to do an angle so we don't have a straight, perfectly straight line, right? So it says all those, the set of points between A and C, including A and C. So if we have all those points right there is a blank. Now, we don't talk about B here, right? In the second half of the sentence from here on, it doesn't talk about P. That's why I crossed it out. We're just focusing on A and C. What does this create here? Does it create a ray? I don't see any arrows. There's no circle. We don't have an angle. This gives us a line segment. Ooh, that was a bad box. But that's our answer. We have a line segment here. It's 2 points and all the points in between it. That's our line segment definition. The line M is shown on the coordinate plane. We have M here. It has 2 points on it, S and T. It crosses my x-axis. It crosses my y-axis. This is the stuff that my brain does when I see these line segments. It says, which is the best definition of line segment ST? Is it all the points on line M? Well, first of all, we're talking about line segment, right? So I'm going to highlight that. This is very similar to what we just did in the last problem. We highlight this. That is my line segment. All points on line M include that arrow. This is not it. The 2 points S and T. Is it just those 2 points? No, it's the stuff in between it too. The point S, the point T, and all the points on line M between S and T. This is our answer right here. Right? Let's just look at the last one. The points on line M starting at point T and extending beyond point S. No, this would be a ray, right? Starting at T and going past point S, that would give us a ray. Next up, refer to the diagram. We have a diagram here. We have 2 lines. We have a line M. We have line N. They are parallel, it looks like, right? We have a ray AB. We have a ray AC. That creates an angle BAC, right? We have a line P, and we can see that we have a 90-degree angle symbol, a right angle symbol, and a 90 degrees here, right? That tells us that they are perpendicular to those parallel lines, right? So which terms are demonstrated in this one? Do we see a circle here? No, we don't. Do we have an angle? Yes, we do. Do we have skew lines? Now, we actually went over this problem earlier in the year. Skew lines are lines that are kind of parallel, but not. So they don't follow each other. They're in different planes, and they cross by each other once. They do not touch, and they will never touch. It's like if you held your arms up in the air, right? Straight up in the air, but then you moved your one arm, maybe your right arm down a little bit. Those would be skew lines. They don't touch each other. They never will touch each other, right? But they're not in this picture. We would need 3 dimensions. Do we have parallel lines? Yeah. M and N are parallel. Do we have a line segment? Sure we do. B to A. That's our line segment. And do we have perpendicular lines? Well, we have that 90-degree angle, and we have that 90-degree angle, so we must have perpendicular lines. Moving forward. Now we're moving into constructions. Now, I made the first half of this review heavy on the definitions and heavy on constructions because of the fact that we haven't seen those in a while, right? A lot of the other stuff that we're going to see, we're going to go over quick and briefly on here because we just did reviews on it. So if you need a review on those, go back to the last quiz review in order to get that stuff, or go back to a previous quiz review to get that stuff. But this stuff we haven't seen too much. So I want to make sure we are good on this, because if it pops up, then we're going to be solid, right? So it says Jericho is making several constructions based on the segment shown. And we have a segment PQ. Part A. Now, it gives us the segment PQ, and we have our arcs above and our arcs below. For his first construction, Jericho made the markings shown using a compass, open to the length less than the length of segment PQ. So it's less than the length of segment PQ. So it's not fully open to PQ. Jericho's markings are useful for the construction of which figures? So it asks for a 60-degree angle, a bisector of PQ, a line perpendicular to PQ, a rhombus with PQ as one of its diagonals, an equilateral triangle with the side of PQ. So one thing we could say here is it's not going to be a 60-degree angle, which is also not going to be an equilateral triangle, because those two things go hand in hand. And the reason it's not those is because of right here. It says opened to the length less than the segment PQ. If he opened it exactly to PQ, we would be able to connect. If you look over on the left side here, you'd be able to connect those to create that triangle, and all 3 of those sides would be equal. This is just an isosceles triangle, but it's not equilateral, right? A bisector, if I sketch this line here, right, this is going to give me my midpoint here, which cuts my segment PQ in half. So yes, that is a bisector. This is also going to be a perpendicular line, right? Now, one last thing, it says a rhombus with PQ as a diagonal. This will give us a rhombus. Let me change the color here. Let's go to purple. In purple, if I drew these lines, now I know, once again, I know they're not perfect, but all of these sides are going to be the same. Why? Because our compass did not change its distance as we made this. Those arcs that were made did not change the distance, so all those sides have to be the same. PQ is a diagonal, so yep, purple, that is going to be one of our answers right there. Now, when it comes to constructions, I know we haven't done much on them. I'm going to put the links of the different constructions down in the information for this video. So down below in the description of the video, I will have links for each of the different constructions that are available that you might have to see, right? Next up, the figure shows a construction of the bisector. So an angle bisector for angle P. We get this construction. It says drag and drop the correct order first to last, right? We can't drag and drop, so we're just going to number them. The first one says name the intersection of the two arcs X. This can't be number one because we haven't created any arcs yet. Draw arcs with the same radius centered at P, right here, that intersect PY and PA. That might be number one. Let's just read the other two first. Using a straight edge, draw a line through P and X. Wait, if we don't have X yet, like I said in the first step, then we can't do this. So that actually might be the last one. And let's read our last in this list. Draw two intersecting arcs with the same radius, one centered at Y, one centered at A. Well, Y and A shouldn't exist to start off with, right? Or they do, but we create those arcs. So this is going to be step one. We want to put our compass centered at P, draw one arc, draw two arcs. That's step one. And then we go to our last step here. We use this as a center, create an arc. Use this at a center, create an arc. And what happens? That creates point X. So we name the intersection of the two arcs X. That's step three. And our last step is to draw our bisector or angle bisector, which cuts these two angles in half. YPX and APX would be congruent. I'm going to write that up here. YPX, whoa, is congruent to angle APX. That's what this tells us here, right? So that is step four, right? I know this information was not necessarily what it's asking us, but it's good to know. YPX is congruent to angle APX. Next up, we have another construction here. This one is a two-parter, right? So it says Leon needs to construct a parallel line, L, that contained point P using a compass and a straight edge. So we have line L and we have point P. So line L and point P. The figure shows Leon's construction. He has line L, we have line M, which is now parallel. We have that, he created a line N, we have point P, we have some arcs, we have arc T, we have arc S, we have arc Q, we have arc R, right? Let's see what steps is going to ask here. Now, I suggest watching the video of how to create parallel lines down below first, and then coming back to this problem and trying it before you watch me explain it. Because when you see someone do it, and I can't do the construction on here, it's going to be a lot easier to understand. It says, which answer choice steps did Leon take to in the correct order, right? So first up, the first thing we have to do here is draw line N. Right, so we're going to draw line N. So this is our only answer here because draw line N is only the first step. And then it goes to draw we're going to draw T, copy Q at point P. We draw S where it intersects. We draw R where it intersects, right? So T, Q, S, R, and then last but not least, you could draw M through the two intersection points right there. Now it says next Leon needs to construct a line that is perpendicular to L and passes through point P. What should his first step be? So let's break this down again. We want it perpendicular to line L and it goes through point P. So what Leon needs to do is place his compass. Now I'm going to go top left here. He wants to place his compass on point P, and he wants to create one swooping arc, almost like a happy face. So he gets two intersection points here, right? he's going to get 2 intersection points. And then he'll create arcs down here using those 2 intersection points. Oh, not like that. It actually should be going the other way. This is just me freehanding, right? So it should be like whoop and whoop. And then what happens? Oh, that's a little off. I know none of this is perfect. This is just an example. He would draw that line down, and that would be perpendicular. Yay! This is all freehand. This is a sketch of what might happen if you watch the video. We'll show you, right? So it says place the compass on line L and draw an arc that intersects point P. No. Place the compass at point P and draw 2 arcs that intersect line L. Maybe because we have an arc, but let's read the other ones. Place the compass at point P and draw 2 arcs that intersect line M. Do we even have line M in this situation? We do not. Place the compass at where arc T intersects line L. No, we don't need that, right? So our only answer is B. There's our answer. Check, check. So it's B for both of these. Wow, that's trippy. Next up, another construction. This should look like a construction we just did earlier. It says the figure shows a geometric construction. The markings at point D were made with a compass open to the length less than the length used to draw the arc from point A. This is our angle bisector, which you saw earlier, right? So remember, he put point A, drew this one big arc that gave me B and C. Use that to draw the arcs to get the intersection point for D. Then you draw the line AD, right? It says, based on the construction, which statements must be true? Select all that apply. AB is congruent to AC. AB and AC. Well, if you notice, this arc is the same here, right? So this first arc is the same. If that first arc is the same, that means it's part of a circle, which means that AB and AC need to be the same because they're both radii of that circle. Next up, BD is congruent to CD. BD congruent to CD. This needs to be true also. So we're going to check that off. The reason that has to be true is because if you switch the length of your compass here, right, or the radius of the compass, when you make these 2 arcs up top by D, then none of this is going to work. And it's going to give you something that is not cutting it in half. AB is congruent to BD. AB is congruent to BD. No, this should not be true. AB should not be congruent to BD. AD is congruent to AD. Hey, this is what we call our reflexive property, which we're going to learn about next marking period. Something is equal to itself. Of course it is. It sounds stupid, but yeah, it is. And then AB is congruent to AD. Just look at that. AB is here. AD is there. Are they the same length? No, they cannot be the answer. So E and C are not it. It's only A, B, and D. Let's look at our next one. Based on construction, which 2 angles must be congruent? I hope we can know this one. It's going to be B, A, D, and C, A, D. So BAD is all my first one. So we need to find CAD, which is going to be D down here. BAD and CAD. It's these 2 angles that are congruent to each other. Next up, using a compass and a straight edge, a student constructed a triangle in which XY is one of the sides. The compass is open to the set length, and 2 intersecting arcs are drawn above XY using X and Y as centers. The intersection of the 2 arcs is labeled as Z. Right? What could be the set length of the compass so that triangle XYZ is isosceles but not equilateral? Not is a key word. So in order to make it equilateral, our compass would be open up to XY. Right? So where it says equal to XY here, that is not going to be it. That will give us equilateral. Now, a general rule is that our halfway point, our compass has to be open more. So this less than halfway, it's not even going to touch. This will not make a triangle. So equal to halfway, that works. Between halfway and XY, that works. Greater than XY, that works. It can't be equal to, and it can't be less than half of XY. Less than half of XY will not give us a triangle, and equal to XY will give us an equilateral. So now that goes to part B. It's to select the correct phrase to complete the sentence. If opening the compass to equal to XY, right there, then triangle XYZ will be equilateral, right? Equal, equilateral. Pretty simple to match those 2 up in your head. Next up, we are moving on to a different topic. This is our distance formula. Now remember, if we have a line that is vertical on our coordinate plane, I could count how long that line is. If we have a line that is horizontal, I could count how long that line is. But if we have a line that is diagonal, either it's increasing or decreasing, I don't know how to count these 2 lines, right? It's only the vertical and horizontal. So that's when we use our distance formula. So here it says a landscaper is putting a border on each side of a triangular garden. She plots the vertices of the garden. -3, or -2, 3, 5, 5, and 7, -3 on the coordinate grid. She estimates that she will need 2 feet of material for the border for every unit of length represented on the graph. So, with this, it says part A, which expression can be used to determine the amount of material needed for the border of the side of the garden represented by the vertices 5, 5, and 7, -3. So what I'm going to do here for you guys is I'm going to write what our distance formula is equal to. So we get D equals the square root of x2 minus x1 squared plus y2 minus y1 squared, right? And the reason this is helpful is because we can then label our points x1, y1, x2, y2. And we could plug those in. So it says x2, which is 7, minus x1, which is 5. So we first want to find the 7 minus 5. We don't have that. Uh-oh. So they actually labeled these in reverse, right? So what they did was they said x2, y2, x1, y1. So now when we look at this, do we have 5x2 minus 7x1? We do. It's our first one. So this looks like it's going to be our answer, but let's double check. Plus y2 minus y1. y2 is 5 minus -3. There we go. We got our answer right there, right? So this is the length of one of the sides. It says the material for the border costs $1.50 per foot. To the nearest dollar, what is the total cost of material to put a border around the entire garden? So we actually need to use this distance formula. So what we could do is we could plug this part into our calculator, right? And I'm going to do that down on my own, right? I have my calculator up. We get the square root of 5 minus 7. Now, make sure you type these in properly if you are typing it in a calculator, right? Use all the parentheses that you need to. Make sure you do everything perfectly, or else it's going to come out not proper. So I do the square root of that, and that gives me about 8.25, right? So 8.25. This is only one side. We need to do this for 2 other sides, right? Our next side is going to utilize -2 and 3, 7, -3, right? So -2, -3. So when I write, let me erase all this up here. When I write that distance formula, right, I'm going to plug it in using that distance formula down below. Square root. We get x2. Let's say 7 is my x2. 7 minus x1, which can be a -2, squared, plus, see those double sets of parentheses because we have that minus and negative, right? And then we get -3. I'm just going to throw that in parentheses to be safe. -3 squared, right? And we need to figure out what that is equal to. So let me plug that one in. Plug it in. We get square root 7 minus -2 squared plus -3 minus 3 squared. Enter. And that gives me about 10.85. 10.85. And then we have to do our last distance. We have one more distance formula. Actually, let me change the color for this one so we could differentiate. 1 second. Let's go purple. And that's going to be for which 2 points did we not match up? Those 2 points in purple right there. -2, 3, and 5, 5. We get D equals square root 5 minus -2 squared. That's x2 minus x1 plus y2 minus y1, 5 minus 3 squared. And we need to figure out what this is equal to. So once again, plug it in my calculator. Now you get 5 minus -2 squared plus 5 minus 3 squared equals, and that gives me about 7.28. 7.28. So down below here, switch colors again. It says material for the border costs $1.50 per foot, the nearest dollar, right? So we need to add all this up first to find the perimeter, which is the distance around the entire garden. So we're going to do 8.25, 10.85, and 7.28. I'm actually going to do this in my head. Let's do some mental math. 5 plus 5 is 10, plus 8 is 18. Boom. 2 plus 8 is 10, plus 2 plus 1 is 13. Boom. 8 plus 1 is 9, plus 7 is 16. Boom. 1 plus 1 is 2. So this gives me 26.38 feet. But now we need to multiply that by that $1.50 to get our cost. So it gets 26.38. And I'm going to say cost equals, this is going to be perimeter here. Cost equals up times 150. Right? So I'm going to do this on my calculator. We get 26.38 times 1.5. And that's going to give me about 39.57. Uh-oh, mister. There is no 39.57 here. But it says, what is the cost to the nearest dollar? So we have to round up here, which would give me 40 is my answer. It's a lot of work, but we got it done. It's just plugging it into that equation, adding everything up, and then multiplying it for the cost. Next up, we are talking about our rotation rule, right? And symmetry. So we talked about this a little bit last week. So let me go to purple here. So it says the diagram shows a regular hexagon. A regular hexagon just means that all the sides are equal. So CB is equal to BA, which is equal to AF, which is equal to FE, which is equal to ED, which is equal to DC, right? The hexagon ABCDEF with the center at O, right? And it gives us an angle here already at 120. Why? Because it says Justine made these claims. The only lines of symmetry for a regular hexagon is of ABCDF are lines that contain one vertex and O. This is not true. And I'm going to just tell you it's not true because why? If we create a line, create a line here that goes through center and connects the vertices, those work, but it's through two vertices in the center. So through two vertices and the center. But also, if we do something like Y here on my my Y-axis, this is going through the midpoints of opposite sides, right? But that also works. That is a line of symmetry. So through two midpoints of opposite sides. That works. Opposite sides, that should say down there. So through two midpoints of opposite sides, right? Now we could do that for any direction, but they're all going to work. Those are the lines of symmetry. So that's where she messed up there. Now, when it comes to where did she mess up? Where did Justine mess up? For my second part here, it says the only angle of rotation that shows symmetry is at 120. This is also not true. So I'm going to get rid of the stuff that I wrote on here earlier. The reason this isn't true is because if we look, ignore these black lines here. If we look and create these red lines from our center to each vertice, because every time this, think of this like a clock and it ticks, it turns, it turns, it turns. If A turns to where B is, so boom, right? Turns to where C is, turns to where D is, turns to where E is. Every time it hits the next point, it's going to look the same. Now, if we do this whole thing, it looks like a circle, which is a 360, right? Full circle. But how many chunks will it look the same? We get 1, 2, 3, 4, 5, 6. We get 6 chunks. Once again, 1, 2, 3, 4, 5, 6. That gives me 6 chunks. We divide these and it gives me 60 degrees. So it's every 60 degree rotation, which means at 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300, and of course 360. Not only at 120, it's going to give you all those. So these are all the symmetry that this regular hexagon has. We got linear symmetry and we have rotational symmetry here. And our last problem, I believe it's our last problem. I don't see on my PowerPoint if it is or not, but let's check. So it says the right triangle in the coordinate plane is rotated 270 degrees clockwise about the point 2, 1, and then reflected across the y-axis to form A prime, B prime, C prime, D prime. Drag and drop the appropriate orientation for triangle A prime, B prime, C prime in the correct position. So first of all, what I want to do here is write down the coordinates for A, B, C, right? Because we're going to need these. It's going to help us out. So first of all, A is at 2, 1. B is at 5, 6. And then C is at 5, 1. Now, how many transformations do we have here? Rotate it and then reflect it across the axis. And we're rotating about the point 2, 1. So that makes this even more complicated. So I'm going to actually make that point in yellow on my grid. We go to 2, 1, and what do we notice? That is point A. So that point's not even going to move, right? So now how do we rotate around a point that's not my origin? Well, first of all, we have to write vectors, right? So my first vector is not, we don't even have to write it for point A. It's going to stay the same, right? So our next vector is going to be, we'll just call it A, B. And that vector is going to look like what? We have to go 1, 2, 3 to the right, 1, 2, 3, 4, 5 up, 3, 5. And then our next vector is going to be A, C. And this is to rotate these points, right? So now this one is going to be 1, 2, 3 to right, 0 up. So we get 3, 0. Now, what's my rule for 270 degrees clockwise? This rule is going to be X, Y. And now this should be the same rule as 90 degrees counterclockwise, which makes me take my negative Y, X. So take Y, move it up front, make it negative, or change the signs. I apologize, I should say make it negative. Change the sign, and then your X. We're not applying this to our coordinates. We're going to apply this to our vectors to get our new coordinates. Now, why don't I have a vector AA? Because that wouldn't make sense. It stays in the same spot. So these new vectors, we're going to apply that rule. We're going to get A, B prime. And we're going to apply that rule to our vector. So vector, move the 5 up front and change the sign. So we get negative 5, comma, 3. So what's my next vector? A, C prime, right? Move the 0 up front. I can't change the sign because it's 0. And then 3 falls to the back. So now these are going to tell us where to find our new points. Let's plot those points right now. Now, actually, I'm sorry. These aren't even the prime points yet because technically, actually what we're going to do is we're going to change everything here. We're going to call this double prime, double prime, double prime, double prime, double prime, double prime. Change everything to a double prime for where the answers say, oh, prime. Because we're doing 2 transformations, it's going to make it a little easier for us here if we call all that double prime. So now I change everything to double prime, right? So we know at least, right? So A prime stays in the same spot. This is A prime. Doesn't move because we're rotating around that point. And now we need to find our next 2 points. B prime, negative 5, 3 tells me 5 left, 1, 2, 3, 4, 5, and 3 up, 1, 2, 3. We're going to put that point right here. And that should be B prime. C is 0, 3, 1, 2, 3. And that should be C prime. And this was our rotation. 9 degrees, or 270 clockwise, 9 degrees clockwise, counterclockwise. Now it says reflect across the y-axis. So now we have to reflect across our y-axis. Now remember how we do that. We count. Which way is my y-axis? Here. Oh, man. Ooh, that was rough. Again. Oh, man. When we reflect, it's cutting through our shape. So our shapes are going to overlap. Let me change the color here. Let's go to purple. And how do we do this? A prime is going to 1, 2 towards 1, 2 away. This is A double prime. Our coordinate for that is going to be at -2, 1. B double prime, C double prime. Just writing these now so I don't have to rewrite it. So C, we count how many? 1, 2 towards, 1, 2 away. And here is C double prime. Now this is going to look confusing because once again, everything's overlapping. And B double prime, 1, 2, 3 towards, 1, 2, 3 away. That is B double prime. Oh, C double, B double. When we connect it, we get a shape that looks like that. Let's write our coordinates. B is at 3, 4. And C is at -2, 4. And there we go. We have our coordinates. So which of these is going to be our correct placement? If we look, we have A prime, A double prime with B double prime above it, or C above it. B is off to the right. So that means our correct placement is this one. We already graphed it, which is like we clicked and dragged it over. We have our coordinates down here to show that we understood, right? And we are good to go. We did our double transformation here. And like I said, that was our last one. So down below in the description of this video, I am going to have the videos for the constructions. If you need to check those out, make sure you do. Make sure you look at your past reviews to help you study for content that we didn't fully cover here if you need more, which might be the distance formula, which might be our transformations, right? We did a lot of transformations, but we just did a review for that, so look that over. And if you have any other questions, let me know. But good luck, have fun, be safe. See you next time.